this video, we'll be covering the properties of power series. So specifically, what we can do when we have multiple convergent power series, what properties are true, and where do those combinations of power series converge. So let's suppose that we have two power series. The first one is Cn x to the n, and it converges to f of x. The second one is Dn x to the n, and it converges to g of x. And we'll assume that they're happening to converge on some common interval I. So this is not useful if one power series converges to like -5 to 0 and another converges from 1 to 5. There's no common interval of convergence. So this only holds if there is that common interval. If so, then you can add the power series. So if you add Cn x to the n plus or minus Dn x to the n, so adding or subtracting, that resulting power series is going to be convergent to f plus or minus g on that same interval. Similarly, if you were to take one of the convergent power series and multiply by bx to the m, where b is some real number and m is some positive integer, you're basically scaling one of your power series. That scaled power series will converge to bx to the m times f on that interval. Okay, next, let's say that you took your f series and evaluated the power series at bx to the m. So you went ahead and substituted that x for bx to the m. Then that power series will converge, and it will converge to f of b to the x to the m. Again, on that same interval I. Okay, next, we've done adding and subtracting. What about multiplying? So let's first define e to n, e sub n to be c0 times d to the n plus c1 times d to the n minus 1, so on and so forth until you get to cn d sub 0. Basically, we are counting up on the indexes on the c's and we're counting down on the indexes on the d's. This is called the Cauchy product, and it's actually how you multiply power series is with the Cauchy product. So if we multiplied our two power series by each other, the resulting series is e to the n, that e sub n, times x to the n. So that is the result of multiplying these two power series, and that Cauchy product series converges to f times g on that same interval of convergence. So yes, we can multiply convergent power series and get a convergent power series. Okay, so that's all the combinations of power series. Obviously, dividing power series doesn't really make a whole lot of sense. So there's no statements about dividing power series, and how we do that isn't necessarily well defined. We'll just leave it at that. It's kind of a complicated issue that you get to in very advanced mathematics classes. So for our last two cool properties of power series, we can term by term differentiate and we can term by term integrate. So if we wanted to come up with a power series representation for f prime, we would differentiate the power series representation for f, and the interval of convergence would be maintained, but you have to manually check the endpoints. So with both integration and differentiation, it's possible to have different behavior at the endpoints for the derivative integral than you had for the original, and so it's something we're just going to manually check in each instance. So the same thing for term by term integration. We can do it, we integrate the power series term by term, and we get the power series representation for the integral of f. Okay, so let's practice using some of these properties. First, let's practice differentiation. So for this example, we are going to use the power series representation f of x equals 1 over 1 minus x, which has the power series representation x to the n. We learned this when we were talking about geometric series. And where does that converge? It converges for absolute value of x less than 1, just kind of a reminder there. So that's our interval of convergence. And we'll find a power series representation for f prime of x. So f prime of x, we know what the explicit formula is for it. F prime of x is going to be -1 times 1 minus x to the -2 times -1, which simplifies to 1 over 1 minus x quantity squared. So that's the explicit formula for f prime of x, and we want to come up with a power series representation. So to do that, we will take our equality, which is that our original f is described by the power series, n equals 0 to infinity x to the n, and differentiate both sides. Okay, it's very logical that we can go ahead and do this. You might want to write this as in a more expanded sum just to kind of get a handle on what's happening. So this series ends up expanding as 1 plus x squared plus x cubed plus x to the n, so on and so forth. So what happens when we take the derivative? We end up getting the derivative of 1 is 0 plus 1 plus 2x plus 3x squared plus so on and so forth, n x to the n minus 1. Okay, so we have a formula here, n times x to the n minus 1, and yes, it's true that we could just kind of use that to write our power series representation. So one possibility that we could do is we could say, okay, our general formula looks like it's n x to the n minus 1. And we need to start at n equals 0 to get that first 0. And then when we get n equals 1, it looks like we'll be on board. Another way to write this, though, would be we could go ahead and describe this as n plus 1 times x to the n. Because if you look at why would we want to include this plus 0? Like 0 plus, is that really giving us any information? Not really. So this power series representation kind of gives us that extra 0 term, which doesn't help us that much. And even though it was easy to generate, if we just, like, notice how the formulas are related, if you just add 1 to each of the n and the n minus 1, we got to the n plus 1 and n here. So which formula would a textbook go with? A textbook is going to go with this one, because it would say that that plus 0 is really unnecessary and, you know, not necessary to express that. So this is the more clean power series representation, if you will. And what interval do we know? It's convergent on at least the interval x less than 1, okay, because our original geometric series was convergent on for absolute value of x less than 1. So now we need to check the endpoints. So the endpoints is x equals negative 1. When I plug in x equals negative 1, I get n plus 1 times negative 1 to the n. And at x equals 1, I'm going to kind of look at both series side by side. They're related to each other. N plus 1 times 1 to the n. Okay, so in this instance, our two series are n plus 1 times negative 1 to the n, and then when we plug in x equals 1, we get n plus 1 for our series. So the cool thing about both of these is if we just take a look at them using the divergence test, which is probably our favorite test ever, if we take the limit as n plus 1 goes to infinity of negative 1 to the n, well, it is certainly not going to be 0. Okay, because the n plus 1 part is going to grow without bound, and the negative 1 part is just going to make it alternate. So if we look at our terms, they're going all over the place. So our divergence test will tell us that it's not equal to 0. And with this one, with the non-alternating series, n plus 1, when I take a look at the limit as n plus 1, a limit as n goes to infinity of n plus 1, we get straight up infinity for this one. So clearly in either of these cases, we could say that by the divergence test, neither series converges. Sometimes people would look at the first series, this one right here, the n plus 1, negative 1 to the n, and they would say, oh, by the alternating series test, this is divergent. That's another argument. It's just another way of looking at it. So either way, that's fine. Okay, so for our final answer, f prime of x is equal to, you want to make sure that you tell someone the series representation as well as the interval on which that series equality holds true. So on the interval, negative 1 to 1. Okay, so there is our final answer for what the derivative is represented by. So what this means is if you, for some reason, were not able to come up with an explicit formula for f prime, think about how useful it would be to at least have some sort of formula. In this instance, we could explicitly differentiate our f of x and come up with what f prime of x is equal to. But in some cases, you can't. And we'll see some of those in future videos, and then you'll see it more in some other classes as well. Okay. Let's take a look at our next example. So for each of the following functions, we're going to find a power series representation for f by integrating the power series for f prime. So let's say, like for our first example, f of x equals ln of 1 plus x. I don't know the power series representation off the top of my head. I want to come up with one. So this is suggesting, okay, hint, hint, take a look at the derivative. So the derivative of ln of 1 plus x is 1 over 1 plus x. And we can write that as a power series because it's geometric. This is kind of like 1 over 1 minus negative x. So this is like negative x to the n. And it converges for the absolute value of negative x less than 1. So that's the same as converging on the interval from negative 1 to 1. And we can rewrite this as negative 1 to the n, x to the n. Okay, so now I'm going to go ahead and write out my terms. It starts off positive with 1, and then it goes minus x plus x squared minus x cubed plus x to the fourth. So it looks like even terms are positive and odd terms are negative. When we integrate both sides, integrating the f prime will give us an f of x, which is what we're looking for, and then integrating our series will give us the series representation. So when I integrate, I get the constant of integration, which we'll write first. So we get some constant plus x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, and so on and so forth. Okay, so we have the constant plus x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. Now we need to figure out what is this constant c. So we will use the fact that at f of 0, so we're going to plug in x equals 0 to both sides. F of 0 would be equal to the constant plus 0 for all these rest of these terms. So the f of 0 should be our constant. So ln of 1 plus 0 should be equal to c. That means that ln of 1 is equal to c, so 0 is c. Okay, so our series is actually f of x equals x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, so on and so forth. And writing a power series representation for that, looks like we need x to the n, and we need an alternating let's see, this is kind of a guess and check for me and probably for a lot of people. So if we start at n equals 0, we will get, oh, we can't because we have division by 0, huh? So we can't start this one at n equals 0 and go on autopilot, but maybe we can start it at n equals 1. If I start at n equals 1, though, this exponent has a problem. So the reason I say it has a problem is you'll get a negative when you plug in n equals 1. And I need to have just positive x. So I need to fix my exponent. Instead of n, we're going to put n plus 1. And that should do it, because then it'll go start positive, turn negative, and go so on and so forth. So here we go. Our power series representation is -1 to the n plus 1, x to the n over n, and we need to check endpoints. So we're checking -1 and 1. So at x equals -1, we have -1 to the n plus 1 over n times -1 to the n, which is equal to -1 to the 2n plus 1 over n. And 2n plus 1 is always odd. And why is that useful to point out? If it's always odd, an odd power on -1 is always going to be -1. So I can say that this is equal to -1 over n. This is, remember, it's ranging from 1 to infinity. We get -1 over n, which is equal to the negative. Factoring out the -1, we're allowed to do that because of our series of numbers properties we learned. Like, you can factor out any scalar number. And this is equal to -1 times the harmonic series. Okay, so you have a divergent series and you multiply your divergent series by -1, you'll still get a divergent series. So this is divergent. Okay, so at -1 we are not convergent, and let's check at x equals 1. We get -1 to the n plus 1 over n, and then times 1 to the n. So I end up with just -1 to the n plus 1 times 1 over n. Okay, so this is an alternating series. So let's go to our alternating series test. Do we have the necessary quantities? 0 is less than or equal to 1 over n, which is less than 1 over n plus 1. And next, the limit as n goes to infinity of 1 over n is equal to 0. So by the alternating series test, our series converges. Okay, so now we've seen an example where one endpoint was convergent, one endpoint was divergent. So our f of x, which was equal to -1 to the n plus 1 over n, x to the n ranging from 1 to infinity, is equal to f on the interval. Looks like -1 no, but 1 yes. Okay, and just to remember what the actual problem was that we were trying to do, we were trying to express the power series representation for ln of 1 plus x. So kind of just to write that back in our notes so that we remember that, ln of 1 plus x, we just got the power series representation for it on the interval -1 to 1. Okay, that one's really, really interesting how that popped out. Let's keep going and look at some more of these properties. So we're going to do this again, but we're going to repeat it on the function tangent inverse of x. So what we know about f prime of x is that we have 1 over 1 plus x squared. At least hopefully you're feeling more comfortable with that at this point. That's the derivative. And what we can say is that this is equal to 1 over 1 minus negative x squared, which then gives us a series representation of negative x squared to the n when negative x squared is less than 1, which is the same as just saying for x squared less than 1, i.e. the interval negative 1 to 1. And if we kind of just write this a little bit more how we would usually see it, we would usually see the negative 1 to the n part factored out, and then we'd get x to the 2n for our power series expansion. So when we actually integrate this term by term, it would be probably helpful to view this in its expanded form. So we start off with a positive 1 minus x squared plus x to the 4th minus x to the 6th, so on. So it looks like our even powers are negative, or sorry, our every other term is negative basically. Okay, so integrating term by term, that means that f of x is going to be equal to the constant of integration plus x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, so on and so forth. And we're going to use the fact that at x equals 0, we will get what the constant is. So if our f of 0, we need the tangent of inverse of 0, will give us our constant. So that is just 0. So our f of x is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, so on and so forth. Okay, so first we'll deal with the alternating part. Negative 1 to the n should make it alternate between positive and negative, but it's going to depend on our index, whether we need to use negative 1 to the n or negative 1 to the n plus 1. We'll just have to wait and see what the rest of our formula is before we adjust that power. So if I want to start at n equals 1, I don't want to go through all the numbers, I just want to go through the odds. So let's try 2n plus 1, because that should give us the odd numbers, and it looks like I could start at n equals 0. But again, I want the power. I want the power on the x to match the denominator. So I'd make this one 2n plus 1. Okay, so then it looks like I can go from 0, and this will work out. So I just check 2 times 0 plus 1 is 1. So that looks good. N times 1 is 2 plus 1, 3, yeah, so looks good. And then we need to check endpoints before we come up with our interval of convergence. So our endpoints were negative 1 and 1. I'm going to check manually at x equals negative 1. We get negative 1 to the n times negative 1 to the 2n plus 1 over 2n plus 1, which is equal to negative 1 to the 3n plus 1. So we've got multiples of 3 and add 1. Let's see, we get multiples of 3, add 1. So the multiples of 3, are they always anything? 3, so 0, 3, 6. They're not always odd. They're not always even. So maybe this is just kind of like the same as going every other, like being an alternating series basically. So we'd get, if I plug in n equals 0, I get negative 1. If I plug in n equals 1, I get a positive. If I plug in n equals 2, I get a negative. Yeah, so it's going every other one. So I can just write this as negative 1 to the n plus 1. Same series, right? Yeah. And noticing that by the alternating series test, we have an alternating series, so we can apply our alternating series test if we note that 0 is less than or equal to 1 over 2n plus 1, which is less than or equal to 1 over 2n plus 3. And the limit as 1 over 2n plus 1 with n going to infinity will be 0. The alternating series test, AST. Implies convergence. Okay, so we're convergent at x equals negative 1. How about at x equals 1? So we get, again, basically the same series. You get negative 1 to the n times 1 over 2n plus 1. We already did the work to check this, so I'd be fine if you just said, okay, it's the same argumentation. Already checked above by the alternating series test. This series is convergent. Okay, so we found out that f of x, which is equal to tangent inverse of x, is equal to negative 1 to the n, x to the 2n plus 1 over 2n plus 1. And that ranges from 0 to infinity, and on the interval negative 1 to 1. Nice. So in terms of adding and subtracting the properties, we kind of use those facts when we did things like right here. Earlier we factored out a negative 1 in like this step right here. But in practice, we're usually not using those properties of combining power series, at least not very much in this class, I'll say. Generally, what we're kind of doing is using this differentiation and integration for the most part. So in the next video, we will go ahead and take a closer look at what functions we can write these series representations for and come up with a very generalized method. So this video kind of covers a lot of properties and tricks, but there's a way to generalize and come up with these formulas for f of x directly without doing any of this, and we'll see you then.